Hi, it's Barbara. These are computer vision worksheets. In this exercise, we are going to get to know two more CNN architectures, VGG and Google Linux. These two architectures both propose two solutions to the problem for how to craft our filters. However, both architectures approach this problem from entirely two different angles. So let's start with VGG. VGG uses the fixed size of filters. All these convolutional layers in VGG network have simple 3x3 filters. And in this exercise, we are going to discover why authors decided to use so small filters. And we are going to answer the question, how many fields from the first image multiply a single field in the last image? Okay, so let's take a look. So so a single pixel in the last image is produced after multiplying a 3x3 kernel by 9 individual pixels in the image of the previous layer. So now when we take a step back, we have to think which pixel values in the previous image created a single pixel in the next layer. So this pixel was created by multiplying the kernel by 9 pixel values over here. And the pixel in the bottom over here was created by multiplying 9 values in the over here. And when we and now let's draw the area that the area of this image that produced the 9 values over there. So these 9 values were produced by moving the kernel over these 25 values over here. And now if we go one step earlier, then let's think which pixels in the previous layer created a single value over here. And these are these 9 pixels. And probably you should be able by now to notice what I'm trying to illustrate right now. And the bottom pixel was created by the 9 values over here. So this entire blue area of 25 pixels was created by moving the kernel over the entire image. So when we go through this process, we obtain a single pixel in the last image by moving the kernel over the 7 by 7 pixels in the 3 layers before. So the receptive field of a single pixel here spans the entire 7 by 7 image. So the receptive field of 3 by 3 kernels is the same as the receptive field of much larger and much more difficult to compute 7 by 7 kernels. And this was very important because when we want to compute the result of 7 by 7 kernel, we need 49. We need a kernel with 49 values. However, when we use smaller 3 by 3 kernels, we can do the same with only 27 values. So using stacks of these simple kernels allowed us to do the same operation much faster. And now let's go to the Google Linux, which introduced something called Inception block. Google Linet offers also pondered on how to craft our filters, which kernel sizes to choose. However, instead of picking only one size, Google Linet offers decided to just go for the to pick several values and calculate them at the same time. So let's see how it works. Here we have a bit simplified inception block to make it easier to calculate. So in inception blocks, we calculate the result of different convolution operations with different kernel sizes, and then we add these results together. We concatenate them to produce a single feature map. So let's start with a kernel with 1x1 filter. So these kernels work similarly to the fully connected layers. So we basically just have to multiply each original pixel by this value. To make things easier, let's just calculate the values for the first row. So we multiply 1 by 2, then we multiply 6 by 2, and so on. And now things are going to get a bit more complicated. Now we have a 3x3 kernel with a stride of 1 and padding of 1. Let's draw the padding. And now to calculate a single value over here, we need to multiply the kernel by values over there. So we have to multiply 1 by 4, then 6 by 3, and then 6 by 5, and 4 times 7. And we get 80. And then since we have a stride of 1, for the next value we have to multiply the kernel by these values. So here we get 80, and then the process is basically the same. So let's just write the final result. And then we have a significantly larger 5x5 kernel, which should be a nightmare to compute. But actually, let's see, we have a kernel 5x5 with a stride of 2 and a padding of 5. And now if you didn't notice that we have a padding of 5, you might have ended up actually calculating this terrible kernel. But if you notice that we have a padding of 5, then the first row of the output feature map is going to be all zeros, because the first 5 rows of the first 5 rows are going to be just zeros. So we are going to get only zeros here. And for the for another operation, we have a max pooling with 2x2 kernel with a stride of 2 and a padding of 3. And once again, we have a padding of 3 and a kernel of 2. So the first row is going to be only zeros. And now let's calculate the final result. And to get the final result, we have to concatenate the values from all the feature map. So for the first row, we have to add 2 to 80, and then we have 2 zeros. And for the second value, we have to add 12 to 128, and so on.